Good morning, everyone. So I was thinking when I saw the schedule that we were on, first thing on the very last day, I thought let's dive into some real deep, nerdy topics for HAPI. Usually at DevDays we cover kind of more high-level stuff or more beginner stuff, and I thought let's go really in the weeds on a few things today. Having had a few drinks last night, I'm sure a bunch of you are in the same boat I am. Now I'm kind of regretting that decision, but we're going to get through this together. Oh boy, anyone watching the recording later, it was the social event last night, so we're all in this together. I am James Agnew. Among other things, I've been leading the HAPI project now for, I believe, 22 years, which is just wild. HAPI is this great community of open source sort of healthcare developers. We've been working together to build software to support healthcare interoperability for a good long time now. I think it's 24 years. We were talking about this on the bus last night. HAPI will be 25 next year, which we have to have some sort of cake for it or something. Maybe we'll have a celebration at DevDays next year to celebrate HAPI's 25th birthday. Anyhow, I'm a big old standards geek, so that's what we're going to do today is geek out on standards. Come on, clicker. There we go. What I want to talk about today is using HAPI at big scale. And I'm talking, in this case today, specifically about the repository model. So, using HAPI with a database to store your resources at really big scale. I want to talk about partitioning, which is a feature that has been around for a while, but has seen some significant improvements in the last year, and I'm going to talk about them. I want to talk a little bit about search parameter sort of optimization and some stuff you can do to deal with search parameters better at big scale. And I'm going to finish with a grab bag of a few configuration options that you may not know about, because there's a lot in there that are really useful for bringing the system up to really big scale. And I'll talk a little bit about what we're still working on there. As background here, so I want to start with the partitioning discussion. So HAPI, for anyone who doesn't know the history of our repository, we started not right at the start of FHIR, but in the really early days of FHIR. We created a server certainly after FHIR had created their initial Spark server, but not that long afterwards. And the goals were very similar with the two. They were really not sort of thought of as production systems at the time. Like, we were building proof of concepts to test the ideas of FHIR so we could bring something to a Connectathon and, test out, were the actual APIs we were designing implementable? Did they work? Were they useful for people? People took these proof of concept systems. I'm certain FHIR had the same experience. People took these sort of experimental systems we were building and brought them to production. And I mean, that's great. It's always fun when people do that. In the early days, people were building pretty small systems. I knew a few people who brought early HAPI to production. And really the biggest repositories we knew about were like these little sort of 100 megabyte repositories. I want to store 1,000 resources for my locations or some questionnaires that have been filled out, those types of things. So they were pretty small databases back then. Fast forward 11 years to 2025. The largest HAPI installation that I know about, and that doesn't even mean this is the biggest one, because of course nobody's under any obligation to tell us what they're doing with the software, but the biggest installation I'm aware of is storing about 150 terabytes of FHIR data. I don't even actually know how many resources they've got in there. I've had messages back and forth a few times with people working at that scale. And getting the system up to that scale over the years has had all kinds of challenges. The state of the art right now, there's a few sort of trends, a few guiding principles that are really sort of guiding how we approach big scale. I mean, obviously there is way more data going into the system these days. We've noticed, and I find this a really interesting trend, but just in talking to implementers and talking to our commercial customers, that type of thing, there are far fewer DBAs out in the field these days. I mean, it used to be that if you were an organization with databases, you probably had a database administrator who did things like optimize your indexes and run your backups and stuff like that. I think increasingly, and I mean especially with the advent of the cloud databases, things like Aurora on AWS and the equivalent on all the other big clouds, I mean, you really can provision databases and manage them without a DBA, but that does mean you don't have that expertise in-house to do things like optimize your indexes and stuff like that. And we're sort of trying to be aware of that. We're trying to design systems that don't need a database administrator to sort of operate. We notice way slower databases. What I mean by that, and this is, I'm curious if others others have had this experience. Everybody is moving to the big cloud stored databases, things like, as I said, Aurora and the equivalents. I mean, they are amazing platforms. I love them to death. We use them in production ourselves quite a bit. We use them to run our own managed service operations and stuff like that. But we have noticed, like the database IOPS, the speed of disk I/O that you get on these cloud databases is in some cases like orders of magnitude slower than we get with on-prem installations that we're running ourselves with, even with old magnetic disks. So, dealing with that fact has been really interesting. You sort of have to understand and design for a system that's going to have slower disk access, which is, it's weird to say as time moves forward, we got slower disks, but that does seem to be a trend that we've noticed. And then finally, and most importantly, and anyone who's maintained a system for 24 years will know this pain, or for any length of time, really. You have to figure out how to make changes, how to evolve the system incrementally without breaking backwards compatibility. And that is a guiding principle for us. We don't want to make changes to the system that will abandon users who, have been running the system for 10 years. And, we can't make a change that says you can't upgrade the system because we've changed these tables and things don't work. And we try as much as possible to say you can't upgrade the system without running a 2-day migration of data or something like that. So those considerations certainly make evolving the system challenging. Doesn't make anything impossible, but it is always a thing we're thinking about. Come on. There we go. So into the nerdy stuff. I want to take a little bit. For anyone who's never looked at our database schema, this is the data. This is a really simplified. I'm not nearly showing all of the tables that sit in our database schema, but among tables that we've got this table HFJ resource, and I suspect a bunch of you guys, if you were running the server, have probably pondered and figured a lot of this stuff out yourselves. But for anyone who hasn't, 3 key tables in the schema. HFJ resource. There's 1 row in this table for every resource in the database, and the most important column in that table is res ID, that's the resource ID. If I've got a patient in there called patient/123, probably 123 is going to be the value in res ID. That's the primary key for that table. HFJ res ver holds a row for every version of that resource. So if my patient 123 has 3 versions, like I created it and then I updated it twice, then there will be 3 rows in that table, and they will have a foreign key relationship back to patient 123 in the resource table. And then the third big table, and again, this is not nearly all of them, but this is the ones I want to talk about today, HFJ res link. That stores your linkages between resources. So if your patient, there we go. If my patient 123 has a practitioner reference to practitioner 7, for example, there's going to be a row in HFJ res link where the source resource ID is 123 and the target is 7. So that's a nice simple version of that database schema. Whoops. There we go. Turning that into a little bit of SQL. Told you we were going to nerd out here. This is a little simplified version of the SQL that we would emit for a pretty basic search. What we're doing here, of course, and I hope by day 4 of DevDays, everyone is totally comfortable with what this search is up to. We're looking for any patients that have a practitioner reference of practitioner 123. And of course, the way that turns into SQL is we're basically doing a join on this ResLink table, looking for any rows that have a target of, that should say 123, not 222. So my SQL doesn't match the query. That's good proofreading of me. But you know what I mean there. And then, of course, we're joining onto the resource table because there's a bunch of good stuff on that table. And that's sort of the way that query plays out when we issue it and HAPI turns it into SQL on the database. Way back in 2019, we introduced a feature in FHIR called partitioning. The way partitioning works is we added 2 columns to every one of what we call the resource-specific tables. In other words, every table in our schema where 1 row or potentially even multiple rows in the table correspond to a specific resource, a specific FHIR resource, we added these 2 columns to those tables, partition ID and partition date. Those tables, they had a couple of interesting properties. First off, they were, the partition ID was an integer, so it was, a number between 1 up to 2 to the 32. The date used a SQL date time type. I'm using, by the way, the Java terms for this. I'm saying integer and date, but pick your database of choice. We use equivalent database types there. Every single row on every table that is about an individual resource will have the same values in those two columns. So for my patient 1, 2, 3, if that patient has 3 versions, all 3 versions will have the same values of partition ID and partition date in all of those columns. And those values can never change, at least not through the API. HAPI-FHIR provides no mechanism for updating the partition ID or the partition date after it's been set. So you set it when you create a resource, and you can never change it after that fact. The idea with partitioning, and this is sort of a theme that we've had over the years many, many times as we've rolled features out in HAPI-FHIR, we always try and design the tools in HAPI to be sort of loose frameworks that are useful for a couple of use cases we can think of, and ideally can be sort of scaled out to use cases we haven't thought of. And we always expect that implementers are going to come up with crazy use cases and hopefully tell us about them so we can start telling other people about them. A couple of use cases we had in mind for partitioning, of course, strict multi-tenancy. And by that I mean, picture like the GitHub model where, you can have private repositories in there under your namespace, and only you can ever see those repositories. And then someone else can have private repositories under their namespace, and I can never see their repositories. That's strict multi-tenancy in that model. Soft multi-tenancy is, sort of a softer version of that. We've got pools of resources, but perhaps they're not being done for security reasons, so people can maybe see multiple pools, and potentially you can actually have links across those pools. So, an example of that might be I've got facility-based data where all the health records from one hospital go in one of these pools, all the health records from another hospital go in another pool. And typically when we're searching, we want to search only by the pool that corresponds to maybe where a specific clinician is practicing. But in some cases, maybe we want them to look in other pools. In some cases, maybe we even want to have references across. Maybe we'll want to have an encounter that sort of indicates that a patient was transferred between facilities. So we want to have a reference between those partitions. That's possible with this feature if you've implemented it as soft multi-tenancy. One other interesting use case we saw was retention management, using that partition date column to effectively store sort of monthly blocks of observations, where every month we want to lop off the block that is a year old, so that we're only ever sort of storing these rotating 12 months of observations. I always thought that was kind of an interesting use case for that. How this ends up turning into SQL, once again, that same FHIR query that I showed you before. I mean, there's not a lot to it. We just end up adding the partition ID selector. I'm sorry, everyone in the back. I know it's hard to see the bottom of the screen, but what we've added there is just an additional to the SQL we add and link.partitionID equals 7, and that means we're looking for everything in partition 7. You might notice that 7 comes out of nowhere. It doesn't actually appear in the query anywhere. You might be wondering, how do we know we're looking for partition 7? So, I'll talk about that in a second. One other concept that's worth mentioning here is this concept of the default partition. Some resources are required to be stored in this special partition, and what we do is we use the value of null in the partition ID column to refer to the default partition. Putting a null in there was kind of a deliberate design choice. I was talking before about how we try really hard to maintain backwards compatibility, and one of the big challenges we had was in layering partitioning on top of the existing database schema we had. We didn't want to make any changes that meant that anyone who was upgrading from a previous version of HAPI-FHIR all of a sudden had things breaking because we had this non-nullable column. So we ended up adding this, we added these columns as nullable. We sort of set the default to not even use partitioning, but we said if you want to use it, we will put values in that column, and we will let your DBAs handle the work of actually applying partitioning using whatever strategies you wanted. We have specific resource types in HAPI-FHIR that cannot be partitioned. In other words, they have to go into the default partition. And that's an important distinction. If you're using HAPI-FHIR for multi-tenancy, for example, there are certain things that you can't have per tenant versions of these resources. It's a pretty extensive list here, and the reason for all of these is just that the rest of the HAPI-FHIR infrastructure hasn't been updated to sort of understand concepts like this tenant should only be able to fetch these resources from this place. To use one very specific example, structure definition. Of course, we'll often pull structure definitions as a part of validation. It would be ideal ideal, of course, if it was possible for your tenants, for you to have 10 different tenants in the system, and each one of those tenants gets their own structure definitions. And when I validate a resource in one tenant's repository, they pull the structure definitions from their own tenant. That, of course, would be an awesome outcome, and I hope we get there eventually. The problem is all of the validation infrastructure hasn't been sort of made partition aware yet. So that's the reason that we can't partition structure definition, is there's a bunch of work we have to do on validation before it sort of becomes feasible to make it a partitionable resource. And a similar excuse is what we use for everything that's on this list. I will say 4 years ago, it was a much longer list. It used to be that we couldn't partition subscriptions, as an example. We closed that gap about 2 years ago, and we've been sort of closing gaps as people ask for them. So, if something on that list is important to you, we'd love to hear about it. We're sort of slowly working through these as people need them. The way that you implement partitioning is with an interceptor. That's generally the answer in HAPI/FHIR to how you implement anything. There are 2 point cuts. I told you we were going to nerd out here a little bit, that we use for implementing partitioning. Storage partition identify create. And this is basically, you write an interceptor that is invoked every time we're about to create a resource, and that interceptor is responsible for determining which partition the resource should go in that we're about to create. There are no rules about how that interceptor would figure that information out. I'm going to show you a couple of examples of interceptors we wrote, just to give you some samples of how you can do it. But the point here is whatever crazy scheme you can come up with, and we've seen some crazy ones, you should be able to write an interceptor that implements that. There is a second point cut, the read point cut, and that's used when the system's about to go looking for resources. There's lots of, maybe we're doing an update, maybe we're doing a search, maybe we're actually doing a conditional create, and there's a conditional URL that we have to resolve. For any of those read use cases, that point cut gets called first. 2 examples of how these things work that I like to talk about. The first is the patient ID partition interceptor. So if you're implementing partitioning and what you want, and you're looking to do it for scalability reasons, you're trying to build a really big database, one way of doing that is with this interceptor. The patient ID partition interceptor puts every resource in a given compartment in a specific partition. So in other words, if I've got my patient 1, 2, 3, maybe that patient has a bunch of encounters and a bunch of observations that all have subject references back to the patient. Maybe they've got all kinds of other clinical data, administrative data, what have you, that has references back to the same subject, to patient 1, 2, 3. This interceptor will put all of that data in the same partition. This is really useful because it means that anytime I'm doing a patient-specific search, in other words, I'm trying to look for observations for a given patient, I'm trying to look for encounters for a given patient, the database, we can write SQL that means that we'll only ever look in one of our underlying database partitions. That is great for scalability. This does require that you take advantage of sort of the native partitioning that's provided by any of the big databases. I'd say Postgres these days is the most commonly used underlying platform for HAPI/FHIR. It's not the only one we support, but it's certainly the most popular. Postgres has a concept that they just call partitioning. You can enable it, and what you're effectively doing is turning any of the tables that you partition into a bunch of mini tables that are stored as separate pools of rows, basically. And turning this on means we can just go to one of those pools to pull down all of the data that we need for a given patient-specific query. This style of partitioning is great if most of your queries are patient-oriented. Most of your queries are looking for data about one patient or one specific pool of patients. We have found in the real world that does tend to be the case more often than not, so this is often a very good scheme. Worth mentioning, though, this is very much not a security style of partitioning. This is very much a scalability style of partitioning. Doesn't mean you can't write a secure system with it. It just means the partitioning isn't giving you security on its own. The second one that I want to talk about is the request tenant partition interceptor. This one's kind of fun. This is for implementing multi-tenancy. You'll notice my sample URL now has this additional little bit, tenant-a. The way this works is we do have a table for mapping tenant names to partition IDs. This exists in our database. You don't have to use it, but you can, and the request tenant partition interceptor does use it. This interceptor will basically look up when it sees this additional bit in the URL. it will look up what's the partition ID, what's the numeric partition ID for that, and it will go to the database and look that up. So this is, if you're looking to do it multi-tenancy, there's a little bit more to it than that. There's a few additional configuration options you have to use, but this is all documented. If you sort of go hunting in the HAPI/FHIR docs, there's a page about how to set up request tenant partition interceptor that talks about the settings you need to get that working and how to actually populate the table with the mappings, these are things you need to do if you want to use that. On we go. So partitioning has been, it's been really interesting. It's been a useful concept. We have run into a couple of limitations with it. Specifically, when people have gone to implement partitioning in the underlying database platforms, for example, to turn on partition tables in Postgres, one of the complaints that we've had is that we don't include the partition ID as a part of the primary keys of our tables. And that is a challenge if you're trying to turn on native partitioning in some databases, Postgres being the best example. If you're using Postgres partitioning, one of their rules is whatever your partitioning discriminator column is, and in this case it's partition ID, that has to be a part of your primary keys. This is a challenge for us because, as I said, we can't go screwing things up for existing deployments of HAPI/FHIR. Changing the primary keys is a nightmare of a migration. That's probably a multi-day migration for anyone who's got a big database, and that's kind of a non-starter. But we really wanted to make this change, so we spent about a year, most of 2024, and a little bit of 2023, implementing effectively a new split mode in HAPI/FHIR, where you can turn on this new database partition mode. You don't have to turn it on, so if you've got a legacy system that's not using it, nothing is changing. But if you've moved to this new database partition mode, your primary keys change. So the idea being that this is really only intended for new deployments of HAPI/FHIR for now. What we do is we include the partition ID in the primary key. We get rid of the possibility of having a null value for partition ID, so we now call the default partition 0 instead of partition null, because that's another rule that Postgres and others have around partition columns. We've dropped the partition date column just because it was fairly rarely used. We ended up finding that I'm only aware of, I think, 2 or 3 users of it, and we spoke with all of them and sort of figured out ways they could meet their uses with just the ID column. Ooh, something just fell. Most importantly, we now include in this mode the partition ID in our table join statement. So if we're joining 2 tables together using a SQL join statement, we will, anyone who knows SQL, and that's probably lots of us, there's an on statement you put in there, and the on will include both the resource ID generally and the partition ID. This is necessary on a bunch of these databases, once again, for really highly performant table joins. And that was, truthfully, that last point was actually the biggest reason that we made this change. We had a bunch of feedback that partitioning worked really well for finding resources when you were sort of going directly to them by ID or by partition or whatever. But once you got into more complicated searches or sets of underscore includes, the performance fell off a cliff because we weren't doing proper joins. So that has been addressed in this new mode. We did, I guess the other thing that we did is we've always sort of relied on DBAs, on database administrators, to sort of make the required schema changes. We have, as of this new version with database partition mode, we include a sample schema that sets up Postgres in partition mode out of the box. So turning on partitioning is a whole lot easier as of HAPI/FHIR 8, which was incidentally our February release of this year. So we're now one release after that. So showing this in pictures, the primary key for all of our tables has been, we've added partition ID to it. Our join statements now include the partition ID as well. That's what that looks like in pictures. That's all for partitioning. I want to talk next a little bit about search parameters. So, I was talking before about, thank you, about our challenges around, around sort of not alienating old users. Another big challenge that we've had over the years is this one. HAPI is one of the reference servers for the FHIR spec. We try to be a really great, comprehensive, out-of-the-box, complete implementation of the FHIR spec. That support, though, I will say, is often in conflict with good performance. A really simple example is we support every single search parameter out of the box that is defined in the base FHIR specification. That does mean, though, that every time you write a patient, for example, you are writing indexes for all of the, I think it's like 23 search parameters that exist on the patient resource, and that slows down your writes. If you know that you're never going to be searching by patient email, for example, maybe you want to turn off the email search parameter. Maybe that's not bringing you value. That's one simple example, but effectively, there we go. We've found that, we've just found that the default settings are often in conflict with good performance. I want to talk for a moment about a feature that a lot of people aren't aware exists in HAPI-FHIR. This is, I will call it an extension to the FHIR spec. This is sort of a proprietary thing to HAPI-FHIR, but I think kind of an interesting concept. The concept is called combo search parameters. I don't love the name that we chose there. It's confusing a little bit because I'm not talking about FHIR's concept of composite search parameters. This is a separate sort of kind of related concept, but not the same thing at all. To explain it, I'm going to use a simple example. We've got a search up here for 3 search parameters. Family equals Smith, gender equals male, active equals true. If you think about those 3 parameters, all 3 individually of those parameters probably match a pretty large pool of people. Like there's probably a lot of active patients, there's probably a lot of males, there's probably a fairly large number of Smiths because it's a common last name. Joining on those 3 indexes in the database can be slow. I mean, databases don't love sort of searching for joins with giant pools of rows on a given statement. So we've introduced this concept of combo search parameters that allow you to index the combination of search parameters that you're going to be using frequently. So if you know that you've got a screen in your UI that specifically requires a user to enter the family name, the gender, and active, true, or false, kind of a contrived example, but if you know that you're going to be using those 3 search parameters together often, you can index the combination together, and you will get a blazing fast search for that combination through a dedicated index. The way that you define these things is by creating a new search parameter instance in the database. Confusingly, you give it a type of composite just because we couldn't actually add a new type to that type as a required binding in FHIR, so we use composite there. But the thing that sort of defines that you're creating one of these combo search parameters is this special extension that you see up at the top, SP unique. You put that up there, you set the type to composite, and you've now created what we call a combo search parameter. The way you define these is by doing that. You can define that combination is required to be unique. This is kind of an interesting feature. If you want to say that there can only ever be one resource in your database that has that specific combination, and we'll often use this for things like identifiers when you want actually a unique constraint on a specific identifier type or something like that. This is how you do that in HAPI-FHIR. And then finally, you create the combo by creating links to all of the underlying search parameters. So we link to the individual family, gender, and active search parameter to create that combo. That's how that works. Kind of a neat concept. Before I was talking about tuning. This is a great big screenshot of all of the patient search parameters. I will say, turning these things off if you aren't using them, giant speed up often. We've seen, if you're trying to do great big writes, you're trying to backload billions of resources in a database, you'll often see a speed up of 30 to 50% if you get your search parameters way down. The typical advice that I will give people, certainly especially if we're working in the US, is I will say, look at the base search parameters that are defined in US core. If that's all you need, and in most cases, honestly, in the US, that is all you need, use that set instead of what's defined in the base specification. You will get very good write performance, and nobody should be expecting, if they're writing a US core compliant system, that you've got search parameters beyond what's defined in US core. Keep going. A couple of configuration items. This is kind of the last big thing I want to talk about, and I'm going to burn through these pretty fast. There are, of course, links to these slides. I want to make sure we save time for questions. But a couple of things I want to mention quickly as you're configuring. First off, if you can, and especially if you're doing a backload, you're trying to do your initial load of billions of data of records into the system, you'll get a pretty significant speed up in the system if you turn off the ability to delete resources. That sounds like a weird thing, like a weird rationale rationale. The reason that this works is the system will not ever allow you to create a resource that has a reference to a deleted resource or to a resource that doesn't exist. We enforce both of those rules because, I mean, those just feel like sensible things, good referential integrity, and don't link to something that's been deleted. The system, though, if we're creating this patient that I've got up on the screen, the system needs to go and do a read first to verify, do we have that practitioner and is that practitioner deleted? We have to go and look them up to find that out. If the system can trust that deletes are never going to happen because they've been disabled, we put a memory cache in place just automatically that remembers the fact that that resource exists and that it has not been deleted. Or if it was deleted, we remember that fact instead and don't even need to look it up again to know that you can't link to it. So pretty good speed up there through use of memory caches if you disable deletes. The second thing, we've got this feature called mass ingestion mode. This is designed for backloads. I focus a lot of these examples on backloads because we've often found in people building big systems, this is their challenge. You know, people don't want to build a system and then have to wait 3 months to get their data into the system. They want to have that, you know, ideally that should happen in days, maybe weeks if you've got a lot of data. And settings like these are the ones that you use. There's a bunch of specific checks that we disable for mass ingestion mode, and really the intent here is you would turn this feature on if you know that you are the only one loading data into the system and you're doing it in a controlled way where it's going to be loaded consistently, nobody else is messing with the system while you do it. In that type of scenario, we can sort of turn off a bunch of the runtime checks we do, and that certainly speeds things up a fair bit. The third is called the match URL cache. This is another memory cache. We use this to avoid repeated lookups if you're doing conditional URLs anywhere in your system. And then finally, index storage optimization. This is all about dropping a couple of bits of data that we put into the database for troubleshooting purposes. Effectively, if you've ever dug into HAPI's database and looked at our tables, you've probably found the search index tables, the so-called SPIDX tables, SPIDX. All of those tables have a column that has the search parameter name and another column that has the resource name. Those two columns, oddly enough, aren't ever used by our searching. We don't need them to be there, but we include that information because it's good for troubleshooting. But if you're building a really big system, every byte counts, and actually you can save quite a bit of storage space by not using those two columns. So turning on this feature is how you do that. Let's go. Okay. I'm totally timing perfectly here. I'm happy about that. I've got 2 slides left. I'm going to tell you about 2 things that we're working on coming up in the next couple of releases to help you deal with large scale. First off, on the database partitioning mode that I talked about, you know, we introduced that in February of this year. We've seen a few people start kicking the tires of it. I'm not aware of anyone who's brought this feature to production yet, to be totally clear. There are plenty of production uses of the old partitioning mode, but I don't know of anyone who've done this with the new mode yet, and that's expected. I mean, this is a really big change, and we're still doing hardening testing of our own. One critical thing that I want to be totally transparent on here: we have not done large-scale testing of database partitioning mode ourselves yet. The commitment we've made to our community is that by our August release, that happens in mid-August of 2025 of this year, we will complete large-scale testing. We're going to do it on several database platforms, certainly including Aurora Postgres on AWS and Azure Cosmos on Azure. So we're going to do a bunch of testing there. I will say, as of now, there is no migration path. There's no way of bringing a system that uses the old partitioning up to using the new partitioning mode. I mean, it could be done by hand, certainly, but that would be a lot of work, and I wouldn't want to do that work myself. We absolutely intend at some point to write tooling that will help people migrate, but we haven't really decided how that should work yet, so we don't have a great solution. All I can say there is more to come. I don't have a timeline for that specific point. I will say, though, we are much closer to having better tooling to enable you to create different database schemas. I showed you that sample schema before. That creates 5 table partitions on Postgres. That's the only option we have right now. We do have a bunch of underlying tooling that's much more flexible. We just haven't exposed it as sort of command line tools yet. That is coming, though, so we'll hopefully by August have that as well. The other project that's going on right now, and I find this really interesting. I mean, we've got 2 parallel projects going on within HAPI right now. One that helps us build, grow bigger, sort of more scalably. And that, of course, is this new database partitioning mode, which is intended to allow you to grow to potentially petabyte scales and beyond of data without having the database fall over. And that's important, of course. But the other thing we recognize is that if we use less space, like we just need less storage space per resource, then maybe you don't even need some of these features to grow bigger. So we do have a bunch of work in this parallel project. Some of those changes have already made it into the product, but a bunch haven't made it yet and are actively being worked on. Specifically, we're going to do a bunch more denormalization of our search tables. I was talking about taking out the patient or the resource name in those SPIDEX tables. An even better solution would be to have a foreign key to a lookup table with those. That is coming. We're going to build that at some point pretty soon. We are actively looking at, could we store the resource bodies, offload them from the database and move them somewhere cheaper, potentially into AWS's S3, Azure's blob storage, something like that. I mean, probably both of those things. I'm hoping that's actually coming by August. I will say certainly that's coming in 2025. Questionable at this point whether that's going to make feature freeze for August, but probably November if not. So there we go. And we are also looking at creating a couple of dedicated index tables for sort of frequently used search parameters that are optimized to those search parameters. The biggest example is identifier. I mean, people search by identifiers pretty much universally. I'm not sure I've ever seen a FHIR repository that didn't need the identifier search parameter. So having it its own dedicated database table feels like a good idea, potentially even with denormalization of the systems and only sort of leaving the values in the index, something like that. We're still figuring that out, but it's actively being worked on. Gender is another interesting one, just because we know there's only 4 potential values anyway, so maybe a dedicated table that uses fewer bytes per gender value would be a good way of doing that. So we're still thinking about exactly how that's going to work, but this is an active project. There's tickets being filed and pull requests going in fairly frequently for this project number 2. I think that's the end of that. So thank you, everyone. I hope this wasn't overly nerdy. I hope this woke you up on a post-hangover day. There we go. I think I have time for questions.
Questions?
Hi, thank you very much. You talked about disabling search parameters for performance, which is a great idea. Is it possible to later re-enable some of the search parameters? Is that a supported feature, or do I need to migrate to a new installation, start from scratch?
This is a great question. It's funny, in my mental model of these slides, I had a slide on exactly that question, and it occurs to me I didn't include it, so thank you for asking that. Disabling search parameters, the way that works, in HAPI out of the box, you get all of the search parameters enabled, and it's kind of confusing because we don't install the search parameter resources in there. We infer that they exist. It's a little bit like when you do validation, you don't have to manually load the base specification structure definitions. They just are automatically available to the validator. The same for your search parameters. And that, in the end, seems a little bit weird because it does mean that, how do you turn them off if they don't exist in the database in the first place? The way that you turn them off today is by creating a search parameter with the given code and base that you want to disable and setting the status to disabled. So you do need to create a search parameter that doesn't already exist. If you know that you're not using the email search parameter, create a search parameter with a base of patient, a code of email, and a status of disabled. Or I think the status is off, actually. That will turn off that search parameter. I recognize 100% that is really a clunky thing to do. This is another thing we're thinking about pretty hard right now, is what can we do to improve the experience of turning off search parameters. I'll say there's 2 things that we're sort of thinking about and hoping to get in fairly soon. One is the ability for you to sort of do a report on what search parameters are getting used in the first place, because of course it would be great if you could figure out, I never use this search parameter, so let's turn it off. That would obviously be super helpful. The other half of that is some mechanism to disable those search parameters without needing to go through and manually create a bunch of search parameters to turn them off. So I recognize it's not perfect right now. That's how you do it. And hopefully we'll improve that over the next couple of releases.
There was someone here. Well,
Hello, thanks for the talks. You go pretty quick on the caches. So you said memory cache, so I'm supposing it's distributed memory caches, right? And I would like to, if you tested it, what is the best configuration for the size, TTL, and what is your hit ratio? Because I'm pretty sure it will be pretty big, pretty fast. So if you have an insight on it, or we can share it afterwards or whatever.
Yeah, there's a great question. So around sort of sizing of the memory caches, I mean, I will say first off, so the caches today are not resizable. We've tried to put sensible maximum values that actually aren't terribly big. We've really, I think in the initial implementation of a bunch of these caches, we sort of assume that when you're doing backloads, you'll probably frequently have the same values coming through. So a fairly small value for those caches is probably okay. And we'd rather have a few cache misses than blow out your memory and have the system go down. So that's been where we've optimized. That's not the end of the story, though. I will say, a thing I didn't talk about today is OpenTelemetry integration, and we've been adding a ton of instrumentation into HAPI for OpenTel integration. One of the things that has been instrumented is those memory caches. So at this point, you can go in there and see how big has the cache grown once it reaches its maximum size. I think for the match URL cache I was talking about, I believe it's 10,000 entries is the max there. So if you see that you never grow to that, then no problem in the first place. You can sort of find out, and the next step to that is to allow OTel to actually resize those caches. That's not present yet, but that is certainly coming, as well as the ability for you to do sort of static configuration on those sizes over time. So more to come on the caches for sure. Much like everything I've talked about, we've got a good start, but we know there's more we need to do.
Hi. Have you thought and abandoned the idea of having partitions by date? Because one of the things that we sloppy developers do is forget that we need a historical file or record. So it can be automatic. All records of a patient will go to a different place. Even by tenant, it will be the dream of the sloppy developer. So just if you have thought of that, or it's not in your book.
Yeah, sort of the flavor of that I've seen in production from a couple of users was exactly that. I mean, anyone who has sort of like these monthly buckets. I was talking about those monthly buckets of observations. That was a common one. I'm doing maybe device readings, or I'm syncing from an EHR. So these are copies that aren't the source of truth for those records. We've seen a few people that sort of were adding, unbounded amounts of observations, and they didn't want to keep them indefinitely for one reason or another. So they sort of built these monthly bucket pools, and with partitioning, could actually just tell the database, drop the oldest partition of the oldest date partition because we don't want it anymore. That was a part of what we did. I was talking before about how we dropped the partition date column from the new partitioning scheme. The discussions we've had so far have just come around to just basically taking that date and putting it into the ID. Using an ID that's like 2024-08 to represent the month and date of 2024 August. And sort of shoehorning it into that column instead. Not a perfect solution, but at least that has seemed workable for everyone who has had that specific use case. I don't actually know if that's what you're getting at, but I would say I'd love to talk to you more about it and see, figure out, are we actually able to accommodate the scheme you've got in mind? As I say, we're still trying to figure out how these things are useful, so more input into it is always a good thing.
Any more questions? No? All right. Well,
cool.
Thanks, James.
Absolutely. Thank you all.